Okay. So let's start the lecture today. In fact, I thought we could start the lecture by discussing just what we were discussing now, which was the following point. We had we discussed previously in the previous lectures this notion that we could understand why, in a sense, the boundary had information about the bulk by using this principle of holography of information. So the question is, can we use that to understand this entanglement wedge proposal? And I'm going to try and tell you how the answer is partially yes, or for the causal wedge, it's probably yes, but for this more complicated case, the answer is probably no. So let me just try and explain that, and that's related very much to the discussion we were just having right now. The question is, let's just start with the causal wedge proposal. Okay, so the causal wedge proposal is the statement that we have this region R. And this region R has information about everything between the dashed line and R. Okay, so that's the causal wedge proposal. Now, here you might already start asking, why is it that gravity was important? Could you have a non-gravitational theory where some boundary region had information about a bulk region of this kind? And the answer is no. But let me just explain what does work without gravity and what requires gravity. So even without gravity, the following is still true, right? The following, it's not at all surprising that if I draw a cross section, so this is time. It's not at all true. It's not at all surprising that if I was to draw like the evolution of R with time in this way, like this is R, but it's evolved with time. Okay, so I'm on the diagram on top, we have a cross section at a single time. Here we have a cross section at a single theta, and we have now the evolution of R with time. So even without gravity, it's not surprising that this. It is not surprising. Sorry. So it's not surprising that the diamond on R has information about the causal wedge in the bulk. Okay. Okay. So this is true just by solving partial differential equations, as we were discussing. Okay, so this is the part which works even without gravity. And in fact, when people write down the so-called HKLL construction, this is what they're doing. They're not using in any essential way the fact that the theory in the bulk is gravitational. It's just a question of solving some partial differential equations, which would work even in a free field theory in the bulk. Okay. So even without gravity, this part, the part below, is not surprising. But there is actually a difference between the figure that you have on the lower part of the screen and the figure that you have on the upper part of the screen. Because the figure on the upper part of the screen states that the region R at a single time, the region R at a single time has information about this region in the bulk. So the subregion duality proposal is not the statement that you take these full causal diamonds, although as I'll explain in a minute, it's equivalent, but it's not, you don't start out by saying, we'll take these full causal diamonds and they have information about the causal wedges in the bulk. But the statement is that on the Cauchy slice, you take a region R and that already has information about what's happening in the bulk. Okay. So the question then from a bulk perspective is the following. You see, why from a bulk perspective, it's puzzling, and without gravity, it would certainly not be true that this region R that one has just at a single time has information about what's happening in the bulk. And another way to say that is from a bulk perspective. So from a bulk perspective, it's pretty surprising that we should have that this region R on the boundary. So let's say now we just have a picture of the boundary. that R can be completed to the causal diamond on R. Do you see? We said yesterday, and I gave an argument in yesterday's lecture saying, in the CFT, if you give me the region R, then of course, the region R can be completed to the causal diamond. That just follows from the fact that the CFT is a local quantum field theory. But from the bulk perspective, if I said, here's my region R, right? And this region R, let's say I think of the region R as being part of the bulk, or being, the region of the bulk which is close to the boundary. Then you would have said, it makes no sense to try and take R and just draw a causal diamond on the boundary. You should take the fact that, in fact, it has also a very small thickness in the radial direction. And there is more information that can come in from the bulk and come and hit R. And this region R, you might have thought, and in a local quantum field theory, bulk quantum field theory, it would be true, that this region R, would not have information about what's happening in the bulk. It would have information about some part in the boundary, but you could have thought in the local quantum field theory that information from the bulk could come and hit R. Okay? So why can't bulk information info enter this causal diamond? And here it is very important to answer this kind of a question, that the Hamiltonian in gravity is a boundary term. And because the Hamiltonian in a theory of gravity is a boundary term, so that answers this question that we have at the bottom. It tells us that the reason bulk information, there's no new information in the bulk. So the answer to this is that in gravity, it can't, it cannot. And the reason is because, it's an elaboration of the arguments we discussed. It's because the Hamiltonian is a boundary term. So it's only in a theory of gravity that it would be true that the region R on the boundary at the same time has information about what's happening in the bulk. But even without gravity, it would be true that the causal diamond built on top of R has information about the causal wedge in the bulk. But the fact that the region R can be completed to the causal diamond without having some new information about the bulk coming and hitting the boundary is only true in gravity. Okay, so I hope this part is clear. So this is only true in gravity. And this is true even without gravity. I just wanted to emphasize this issue because sometimes in ADS-CFT, this is just treated as something that is obvious. And in fact, in yesterday's lecture also, I mentioned that if you think of the region R in the boundary, then there's no distinction really in thinking of whether you have R or the causal diamond that's built on top of R. And so from the ADS-CFT perspective, it might just be that it's obvious you can shift between the two pictures. But in fact, it is important for this story, as it is in any aspect of holography, that the bulk is gravitational, and it is important when you think in terms of the picture above. Of course, if you think in terms of the picture above and you try to reconstruct operators in the bulk in terms of operators in R at the same time, then you cannot write down a simple smearing of the kind that we were discussing previously. Okay? So if you try to do, at t equal to 0, there is no formula that says that phi tr omega is some integral of O t prime omega prime with some k at t prime equal to 0. So there's no formula that says that you can write down a linear transformation of the field at time t equal to 0 in terms of the field in terms of the boundary field at time t equal to 0. So this is not a linear transformation, but it is nevertheless true that the field phi at time t equal to 0, or within the causal diamond, can be written in terms of operators at t equal to 0. So this does not hold. I should actually write not equal to. It can be written in terms of complicated operators at time t equal to 0, and those complicated operators have to involve various insertions of the boundary Hamiltonian, as we discussed previously. Okay, so at time t equal to 0, you don't have a simple linear formula of the kind, but you do have a simple linear formula if you include the entire causal diamond. Okay. Okay, so from this perspective, if you wanted to understand one aspect of subregion duality, I think one could plausibly extend, although we have not done it in detail, but one could plausibly extend the arguments that we gave previously to argue for this principle of holography of information, to argue for a refined principle stating that, subregions on the boundary have information about causal wedges in the bulk. But for the other pictures that we drew, which was this other picture that we drew, where you had this region, and we said that in some cases, if you take R to be the union of two intervals on opposite sides, then in fact this might have information about all this, which goes well beyond the causal wedge. This is something that I think is not understood properly and does not look like it would be explained just by saying that the Hamiltonian is a boundary term. Maybe there is a clever argument that allows us to make this picture clear as well. But in fact, I think it would be nice to have like a direct Hamiltonian understanding of this picture. And we do not actually have such an understanding, although I think we could, we do have such an understanding for the causal wedge, but not for these larger entanglement wedges. So as we discussed yesterday, the argument for this, comes from a boundary relative entropy is bulk relative entropy kind of perspective, but it's in some sense something rather mysterious, which I think it would be nice to understand better. Okay, and as we discussed, for this case, we can't even write down like simple linear transformations of the bulk and the boundary, and we have to at all times use some complicated transformations, even if you include the causal diamonds on the boundary. To write down the operators in this bulk causal wedge, you need to write down some complicated operators, some complicated transformations. Okay, so that is all I wanted to say about this. I now want to move on to other aspects of the island proposal. But before I do that, are there any questions first? And then I can go on if there are any questions about this part, about this entanglement wedge part.
I have a question.
Yeah, sure, yeah.
But so how is the region, how is the causal wedge defined?
Yeah, so we basically we want to define it as the part which is in causal contact with some part of the causal diamond. So it's the way we defined it yesterday. So if there's
that was actually probably my actual question is this causal wedge proposal the same as the proposal of the subregion duality? Is it the same statement?
No, the causal wedge is smaller. So the causal wedge is this part. So the wedge we have right now is the entanglement wedge, which is bigger than the causal wedge. So the subregion duality statement is that the boundary region R knows about the entanglement wedge in the bulk. The causal wedge duality is something which is smaller, which is the region which is here, and that is so that's this. This is the causal wedge, the region in blue, and the region outside it, which is also like shaded, is the region which is so the region in red is the part which is outside the causal wedge, but still inside the entanglement wedge.
Okay. Yesterday we identified this entanglement wedge by selecting the minimum extremal surface, right?
Yes.
So how do we select the causal wedge here again? Sorry.
The causal wedge is just selected by causality argument. So it so happens that in MTADS, the extremal surface, the simple extremal surfaces also coincide with the causal wedge. But you're right that the simple extremal surfaces were drawn by drawing geodesics, but the causal wedge is just drawn by taking the boundary causal diamond and looking at what part in the bulk you could get to by shooting light rays from there. So that would be. But you're right that it so happens that the simple entanglement wedges that you have coincide with the causal wedge, but then there is more complicated entanglement wedges that are bigger than the causal wedge.
Okay, thank you. It's clear.
Okay, great. So now I want
to. Sorry, I had a question about this subregion duality from the point of view from this holography of information, because for this holography information, we needed the Hamiltonian to be a boundary term, but there the boundary we need to integrate over the entire boundary. So a subregion of the boundary does not have information about the Hamiltonian. Right?
Yeah.
So in that sense, how can there be subregion duality from that perspective?
Good, thank you. So indeed, when we made the argument by invoking the entire Hamiltonian, and one would have to make a more refined argument for this case. But we know a little bit more about than the fact that the Hamiltonian is a boundary term. We in fact know that the Hamiltonian in gravity is the integral of some local density which is integrated on the boundary. So it's a little bit more than just the fact, the Hamiltonian is not just some arbitrary non-local operator on the boundary. It's the integral of some density. So there's a Hamiltonian density which you can define on the boundary, which gravity tells you to do. And the claim would be that if you were to take the part of the Hamiltonian density that's integrated on this part, R, then that would be enough to tell you about the information in the bulk. You're right, we would have to make a more elaborate argument, which we certainly didn't make in these lectures. But I think such an argument can be made. You're right, it uses something slightly more refined than the fact that the Hamiltonian is a boundary term. It uses the fact that the Hamiltonian is an integrated boundary density. So one would have to make, but I think such an argument can be made. But for this larger wedge, I don't know how such an argument can be made.
Okay, thank you.
Okay, thanks. Great.
Yes.
Good. So now I wanted to say a little bit about how how one might go about deriving this formula. In fact, the full derivation is not something I wanted to do, but I just wanted to introduce in these lectures at least the notion of the replica trick, because I think if you were to try and read the literature, that is something that you would encounter all the time. And it's explained, of course, nicely in many reviews, but I thought I would review briefly, just as a technical aside, what the replica trick is to compute entanglement entropy. And I wanted to sketch briefly how the replica trick can be used to derive these proposals that we looked at yesterday. Okay. So that's what I want to do next. So let me just explain first what the replica trick is. Okay, so what is the replica trick? So before actually we talk about in these discussions of the replica trick and using the path integral to compute entanglement entropy, it's useful to always think of the states. We've been thinking of states as these vectors in the Hilbert space, but it's useful to think of the state even in a quantum field theory in terms of a functional of fields. Okay. So we think of the state as a functional of fields. And I hope all of you are familiar with this representation. This representation tells us that if I give you the fields, so I'm here, this is at a fixed time. Okay, so let's say we are always at time t equal to 0. So x, when I write phi of x, I don't mean I mean that we are always at some fixed time t equal to 0. What this means is that, I can think of a state in many ways. Often we think of a Fock space when we think of quantum field theory. But in fact, there's another way to think of states, and that is that you give me a field configuration and I'll give you a number, and the state is a machine that assigns to every field configuration a number. So it doesn't assign to every momentum configuration a number, so it doesn't assign to phi dot a number, but assigns to phi of x a number. And of course, there would be another representation which would assign to pi of x, the conjugate momentum, a number. But it's convenient to think just in terms of a functional that assigns to every field configuration a number. Okay? So it's very convenient to think in this context, particularly for path integrals. And that's because the path integral, or the Euclidean path integral, gives you an easy way to understand what the vacuum state is in this language in terms of thinking of a functional over field configurations. Okay? And the way one does that is we take the following path integral. So we take the action, and let's say we have some fields phi. We integrate over all fields phi, and we do the path integral over the half plane. So we do the path integral from from Euclidean time t equal to minus infinity. So let's write phi of x, and t Euclidean is equal to minus infinity. So let's put some boundary conditions. It actually doesn't matter what boundary conditions we put at t equal to minus infinity, but let's just put boundary conditions which are that the fields die off at t equals minus infinity. And then we can evaluate this path integral and ask, what is the boundary condition that we get at Euclidean time t equal to 0? I'm abusing notation a little bit, but when you see an x comma 0, that's a field which is a function of both time, Euclidean time, and space, and phi of x is just a field configuration at a fixed value of Euclidean time. Okay. So this is a well-defined path integral. I have now given you, it's a path integral that I'm doing from TE equal to 0 all the way on the Euclidean half plane to TE tends to minus infinity. So I'm doing it on the lower half plane, or you can think of the upper half plane if you like. So I'm doing an integral, path integral, and this gives me for every boundary condition I put in the future, which is at t equal to 0, it gives me a number. It gives me a number because I do the path integral, and depending on what boundary condition I put in the future, I get a different number. By future, I mean at t equal to 0, I get a different number, and I can call this psi of phi of x. Okay? So the question is, what is the state that I get in this way? So let's say I do this Euclidean path integral, I get some functional. The question is, what is this functional? Okay? So in fact, this functional is nothing but the vacuum state of the field theory. It's not normalized, but otherwise it's just a vacuum state. And the way to see that is to remember that the path integral, if you do a path integral over Euclidean time tau, then what you evaluate is this kind of a configuration. So if you do a path integral, so this is a path integral over Euclidean time tau. Then the matrix element that you're evaluating, if you do the Euclidean path integral, is e to the minus h tau, where h is the Hamiltonian. Okay? So now in this matrix element, we can put in some complete set of energy eigenstates, right? And you would just find that this looks like sum over E and e to the minus e tau. Okay? And it's clear that in this integral, if I take tau to infinity, then there is a single state which dominates, and the state that dominates is the state which has the lowest energy, and that is the vacuum state. Okay? So if you think of this integral, if we think of this as a function of phi 1 of x, so there's a phi 2, but let's say we think of it as a function of phi 1 of x, then it's clear that what this is giving us what we are getting is some number, there's some number which depends on phi 2, that's some normalization constant that depends on the boundary conditions we put on the other side. But other than that, we're just getting phi 1 of x and 0, where this is the vacuum. Okay? And therefore, if you do the path integral over the lower half plane, as we're doing here, then this wave functional that you get is the Schrodinger representation for the vacuum. Okay? So that's why this is the vacuum state. Okay, so this is a way where one can understand the vacuum state using path integrals. And if one wanted to write down a representation for the vacuum state, this is a convenient way to write down a representation. Okay. So now I want to explain how one can write down a representation not just for the vacuum state, but in fact for a density matrix as well. Okay, so we said that if you do the Euclidean path integral over the lower half plane, you get a representation for the vacuum state. But let's say we wanted to do something else. Let's say we have some interval, or some region on the plane. And let's say I put some and I want to ask, here is my region R, and this is my R tilde. And I want to ask, what is the density matrix associated with R when the state is the vacuum? So that's a reasonable question I can ask. It's an important question if I want to compute the entanglement entropy of different regions in the vacuum state. By the way, it doesn't have to be the state of the vacuum. Often people consider thermal states, but for simplicity, let's just take the vacuum state here. So one could ask, what is the density matrix that corresponds to the region R when the full state is the vacuum? Okay. So even when the full state is the vacuum, the density matrix that corresponds to the region R might be non-trivial, and it might be non-trivial because you have to trace over this R tilde, and R tilde might have various kinds of entanglement. And when you trace over R tilde, you'll get something complicated for R. And in general, it's quite hard if you try and take a quantum field or take the Fock representation to try and ask what is the density matrix that's associated with the region R. It's something that's hard to compute explicitly. But in terms of the path integral, it's quite easy to write down at least formally an expression for what this density matrix is. And the way one writes down an expression is the following. See, you see, I said in the past that I said earlier that if you wanted to write down the vacuum wave function, so let's say you wanted to write down the vacuum wave function, right? So I said this could be done using a path integral. But of course, what is the density matrix? Right? If I wanted to write down the density matrix for the whole state, then of course what I would do is I would write down, one more wave function, the same kind. And this would give me the density matrix as a function of phi and phi tilde. Right? This is the density matrix for all the fields. Now, if I want to trace over R tilde, then all I need to do is I need to set like phi of x equal to phi tilde of x in the region R tilde, and I need to integrate. Right? And of course, in the region R, I'm allowed to have whatever I am allowed to have. And yeah, I just need to set phi of x equal to phi tilde x in the region R tilde and integrate over all possible values in the region R tilde. Okay. So you can see that one simple way to do that is as follows. Let me just write down the answer because it's simpler to just write down the answer and then we can discuss it. So let me use alpha and beta because this alpha and beta now run only over x. So alpha of x, beta of x have domain x, have domain r. So these are not, so I was writing phi earlier. Let's just now think of functions on R. So the claim is that this path integral is given, this density matrix is given by doing the path integral, but in the following way, just with these boundary conditions. Where what this means is that we take the plane, the full plane, we make a cut in the plane in this region R. On the upper side of the cut, we impose the boundary condition that the field has to be beta of x. On the lower side of the cut, we impose the boundary condition that the field has to be alpha of x. And we just do the path integral over the rest of the plane. So we just do the path integral everywhere else. Okay, so I hope it's clear. I won't shade everything. Okay, so we just do the path integral everywhere, and except that on the plane we make a cut and we put some boundary conditions on one side of the cut and some other boundary conditions on the other side of the cut. The reason this is clearly the correct prescription is that if I had, instead of doing over the whole plane, if I had kept the Cauchy slice, then you see if I had some boundary conditions here, let's call these alpha tilde of x. And I thought of doing the path integral only over the lower half plane, then this would give me the vacuum state for the field configuration which had alpha of x on R and alpha tilde of x on R tilde. Right? Correspondingly, if I wanted phi star, I could do the path integral over the upper half plane, and then that would give me something which had the field configuration beta on R and maybe beta tilde on R tilde. And now if I want to trace over R tilde, what I should do is I should set beta tilde is equal to alpha tilde x. So I should glue this plane together on the complement of R, and then I need to integrate, because I need to do a trace, I need to integrate over this beta tilde. But if I glue them together and I also do an integral, it's clear that that's just the same as doing the path integral on the entire plane, except for this cut in the plane with some boundary conditions put in the cut. Okay, so that's why the formula that we have on the top of the slide gives you an expression for the density matrix in the vacuum state for a quantum field theory. Okay, good. So far, so good. If I'm not being clear, I assume many of you have already seen this, but if there are questions about this, I'm happy to answer them here.
Just a very quick question, but
yeah.
This is a purely field theoretical path integral, right? We didn't include it here because of the factorization.
Yes, this is a purely field theoretical path integral. Absolutely.
Thanks.
Okay, great. So now, what do we want to compute? Let's say we wanted to compute now rho, and we managed to compute rho, and let's say we got a little ambitious, and we said, by the way, I should say that this is unnormalized, and it will be important in a minute that we normalize it. So this rho right now doesn't have trace of rho is equal to 1. So we need to put a constant up here to normalize it, which we will put in a minute in our formulas. So now let's say we say, well, Fine, we computed row, but we get more ambitious and we say we want to compute trace of row to the n. Okay. So how would we compute trace of row to the n? Well, it's very simple. Let's take n planes. So, instead of one copy of the plane, let's just take n planes. So here's plane 1, and I have these cuts. So I'm drawing the cut as a double line, but really it's one cut. This is just to indicate that I have different boundary conditions on opposite sides of the cut. So this is plane 1. Let me take plane 2. And now, you see, when you take trace of row to the n, what you're really doing is you're multiplying row with itself some number of times, and then you're taking the trace. But how does multiplication work? The way multiplication works is, in matrix multiplication, or if you have a functional, the way you multiply is you take this density matrix, and then you take another density matrix, and you set the row of one to be the column of the other. So that tells you that you should do the path integral on a second plane, but with beta now put in the lower cut and maybe some gamma put in the upper cut. And then you take a third plane and so on. And now you put gamma on the lower cut. And now you need to do a trace. So you need to, glue back the last index back to the first index. And therefore you put alpha here. So this is trace of row cubed. Okay. And you do the path integral. Okay. So now we are doing the path integral not on one plane, but on some plane which, on 3 copies, which are glued together in this way. Okay. So we have a complicated surface to do this path integral. It's like a multi-sheeted surface. So you have one surface, you have another surface, a third surface. But these surfaces are not just independent. It's not just that you're factorizing and you're doing an integral and multiplying the two. You have to glue these surfaces together in the right way. And the way you have to glue them is indicated on the slide. Okay. So you have to glue the top part here to this part here, then you glue this part here to this part here, and then you glue this part here back to this part here. Okay. I tried to make a paper model of this today afternoon, but I failed very badly. Maybe some of you who are good at this can make some nice paper models of this. But it's actually nice sometimes to be able to think of this concretely. But in any case, it's a simple prescription which says you should take this multi-sheeted plane and you should glue things together, and that gives you the trace of row cube. And of course, if you wanted to compute trace of row to the n, you should take an n-sheeted plane, and that will let you compute trace of row to the n. Okay, now remember I said we had to be careful about the normalization. So in fact, this that we have here is also unnormalized. In fact, trace of row to the n, we would write as Zn by Z1 to the power n, okay, where this is the path integral on the complicated surface that we have here. On this surface. And this is the path integral just on the first surface that we had, just the path integral on the entire Euclidean plane. That's why I write Z of 1. And you see that, I had to divide by Z of 1 because that is what would ensure the trace of row was 1. If I took this expression and I divided it by 1 over the Euclidean path integral on the whole plane, then it's clear I would get something which had the property that trace of row is 1, and that is just Z of 1. Here I'm computing trace of row to the power n, and therefore I need to divide by n factors of this Z of 1. And it's clear that if you divide by n factors of this Z of 1, you will get Z of 1 to the power n. Okay? So trace of row to the power n is given in the path integral format in this way, where you do Z of n, you do this path integral over the surface, and then you need to normalize by dividing by Z of 1 to the power n. Okay? So that's a formula now for trace of row to the power n. Okay, so now that's we are almost done with the formalism that we wanted to develop. You see, we now want to develop not just trace of row to the power n, but we want to compute the von Neumann entropy, and the von Neumann entropy is trace of row log row. Okay, so now how would you compute a trace of row log row? So if you wanted to compute trace of row log row, you see, one way to compute it is as follows. We know how to compute trace of row to the power n, right? But we don't know how to compute trace of row log row because log row, doesn't have some nice simple representation. So we have a matrix representation for row. We can multiply it with itself, but we don't have a nice matrix representation for log of row. And therefore, you might have thought, maybe we're out of luck. We can't do trace of row log row. But in fact, there's a clever way to try and compute trace of rho log rho. And that is that we write down the following limit. Okay? We compute this trace of rho to the n, and then we write down the following limit, log of trace of rho to the n. Okay. Now you see that if you write down this limit that you have here, then this limit, you see that if you take the limit as n goes to 1, this goes to 0. The term below goes to 0 because clearly it goes to 0. But also the term on top becomes log of 1 because you are taking trace of rho to the power 1, which you know is going to be 1, and therefore log of 1 is 0. And so we have a situation where both the numerator and the denominator are going to 1. And therefore the correct way to take the limit, of course, is to differentiate both. And if you differentiate both, you will find that the von Neumann entropy is just given, I hope I got my signs right, is just given by this. So I just inserted the formula that I had for trace of rho to the power n, and then I took this limit, I did the derivative, and if you do the derivative, of course, the derivative of the denominator is just trivial, and you have to take the derivative of the numerator, and if you do that, you will get this formula for the von Neumann entropy. Okay. So this gives you a path integral way of computing the von Neumann entropy, because everything that you see in the formula in front of you can be computed via path integral. Of course, Z of 1 can be computed via path integral. It's just a normalization factor. But Z of n can also be computed by a path integral, as I just explained previously. And once you do that computation, you need to then, that computation only works for integer n, but you need to analytically continue that computation for all real n, and then take the limit after taking a derivative n equal to 1. Okay, are there any questions about this part? So this is the replica trick in a quantum field theory, which is used to compute entanglement entropies. Okay, so now how is this relevant for what we've been talking about holographic entanglement entropies? So you see, the question previously was whether this works for gravity, and of course, as it stands, it doesn't work for gravity, because in a theory of gravity, we need to be more careful about doing all of this. But there is a way where for holographic theories, you can apply this replica trick and use it to compute the entanglement entropy of holographic theories. So the idea is as follows. You see, in holographic theories, we know that if you do some path integral, if you want to do some path integral on the boundary, there is a general prescription from holography that says, well, you can try, there is a way also to do that path integral by doing a bulk computation. But in the bulk, we can often get away by doing a saddle point. Okay? So the idea in holographic theories is that we try and find, so to compute holographic entanglement entropy, so we replicate the boundary as described and find a bulk saddle which has the right boundary conditions. I mean, by right, I mean these replicated boundary conditions. So sometimes the way this is conventionally drawn is, we draw this replicated boundary in this way. Okay. And then we look for a bulk saddle. So this is the bulk saddle. This diagram, could be made better, but it's just indicative. And what we do here is we have this replicated boundary, and corresponding to this replicated boundary, we look for a bulk saddle. And if we can now compute on this bulk saddle, the bulk action, then that is supposed to give us an approximation to the boundary replica, to the boundary integral. And that is how we use the bulk to compute the boundary values of Z of n and log of Z of 1. Okay. So we evaluate the bulk action on this saddle. Okay. So I hope the point is clear. we have a formula. The formula actually tells us that we should compute, it gives us a path integral representation of what we should do to compute the entanglement entropy. We cannot directly use the formula in any way in the bulk. In fact, as I described yesterday, the question we are interested in asking actually is a non-gravitational question. The question we are asking is, what is the entropy of some region on the boundary which does not have gravity? But in holography, we can use the trick. The trick is that holography tells us that to compute boundary path integrals, you can instead look for bulk saddle points in the approximation where holography is valid. And therefore, the idea is you write down this complicated boundary, and then you look for the bulk solution that has the right boundary conditions. If you can then evaluate the bulk saddle point, then you would be in a position to evaluate this boundary integral that we have. Okay, now, so far so good. So far, these are generalities. If there are any questions about this last thing I said, please stop me. Otherwise, I'll go on.
Suvrat, there's a question in the chat.
Question chat. Which analytic continuation is used? Yeah, so so in general, if you know a function or integers, a function satisfies certain properties, you can continue it analytically. So this is the standard thing that we've been doing from the time of Thoth. If you know some function, you know it for all integers, and provided it obeys some additional hypotheses, you can continue it to real n. So basically, you need to ensure that you're able to rule out functions like sine of pi n, which would vanish on all the integers, and so you need to make some arguments for how you expect this entanglement entropy to behave on the complex plane, and if you can make the right arguments, then you'll be in a position to continue the function to real numbers as well. Okay, so now yeah, the question, yeah.
Okay, yeah, question because. So if I understand it correctly, you try to say something fine-grained on the boundary, right? Because you're looking for the von Neumann entropy.
Yes.
But you phrase this fine-grained question in terms of bulk variables, but if you take a saddle point approximation of these bulk variables, how can you still say something so fine-grained on the boundary? Because it seems this by doing a saddle point approximation, all the fine-grained information is lost.
Yeah, I guess, yeah, that's a good question. In principle, I don't know if I have a very clear answer to this question. It so happens that the entanglement entropy that you compute in this way satisfies various checks, and it satisfies a large number of checks. I mean, as I'll say in a minute, we use this in fact to get back the Ryuta-Kinagi formula, which satisfies a large number of checks. But you could have asked this question. You're right. You could have said, how do you know that there isn't something that messes up the computation? And it could have been, but I think that I don't know of any completely clear answer to this question, except for the fact that it has been checked in many cases, and the answers that we get make sense. Yeah, it would be nice to have a clearer answer, but I don't have a clearer answer than that. I don't know if someone else on the call has a better answer. Please feel free to go ahead and give it. Yeah, I think actually there isn't. Well, I think it would be fair to say that there isn't you're right that it looks like in the bulk in gravity we are doing something coarse-grained. Whereas the von Neumann entropy is like a fine-grained object. So you could say, why is it that gravity is somehow clever enough to give us the answer to this fine-grained object, right? How does gravity know how to average things? And somehow it does. Somehow it gives us the right answer. And you're right that in some sense the gravity path integral is clever enough, or just doing this Gibbons-Hawking kind of trick is clever enough to give us the right answer. But I don't know if any completely rigorous justification. You're right. You could have said that maybe this doesn't work, and if it had not worked, you would have said, no, look, you're doing something so crude, and that's why it didn't work. But in many cases, it does happen to work. Although what the question that was raised could be important. It could be that in some cases the formula fails, or this technique actually fails, and then these issues might be important. because it's true that the situations in which this is being checked are situations where we either take the vacuum of ADS or we take some simple states, like we take a thermal state in ADS. So we often end up taking states which have some symmetries, because those are the states when you can compute the bulk and the boundary, or we often end up taking some simple states and then making these checks. And it could be well the case that if you do something in a more complicated state, or you think of more, there's an infinite space of states. If you think of maybe even generic states, then maybe there's a problem in using this prescription. And you're right that it would be. I don't have a better answer to that. It's a good question, but okay.
Thank you.
Yeah.
So there are two more questions. One is,
Yeah, sure,
is this boundary the same as the multi-sheet picture you drew before?
The boundary is the same as the multi-sheet picture I drew before. I now wanted to draw the boundary and also a bulk. So apart from the multi-sheets, there's also some bulk that lives, and that's why this is the conventional way. This is the conventional way. This is a cartoon in which this is depicted. That you have a multi-sheeted boundary and you want the bulk to asymptote to that. One more question is, could you repeat the explanation of the last sentence about holographic entanglement entropy? Yeah, so you want to compute a boundary path integral. And the general prescription of holography is that you can also do that via the bulk, and that is how holography was initially formulated. So how do you do it via the bulk? Well, in the bulk you can't compute the full bulk path integral, but you can say we can compute the bulk path integral in a saddle point by just evaluating the right classical solution, and then by evaluating the action on that. And so that's what you try and do here. In fact, I'm now going to explain how we use the formula to derive it. In fact, it's very rarely the case that we are actually able to compute for this replicated boundary the bulk saddle. In some very rare cases, we can set up the computation, but in general, we don't actually follow this procedure that I mentioned, where you take trace of rho to the n and you compute trace of rho to the n for all values of n in some way, and then you look at the answer and then you say, now we can analytically continue it. In fact, what is done is that you try and analytically continue directly near n equal to 1. Okay, so the procedure that is adopted, and this is a sketch of the derivation that was first provided by Maldacena and Lukowitz of this formula. So the idea is that for n equal to 1, okay, so let's say let me take this figure and copy it through. Okay, so we have to do this, but we need to now, we only need the answer near n equal to 1, right? Because the formula instructs us to take a derivative of the answer near n equal to 1. So the claim is that for n equal to 1, the bulk metric is ADS. Okay, now we need the metric near n equal to 1, right? If we knew what the metric was near n equal to 1, then we would be happy, because if you had the metric near n equal to 1, we would be able to evaluate the saddle. We'd be able to evaluate the saddle. And so the idea is that we analytically continue the metric itself. So we analytically continue the metric. And the idea is to one which has small conical singularities, but which has small conical singularities. Again, the singularities are proportional to n minus 1. So you take the original ADS metric and then you analytically continue it away from ADS to a metric which has these conical singularities. Now, on this analytically continued metric, we compute the bulk action and we get the answer. Okay. Now, this is the procedure that is adopted to do this computation. I should add that we knew we are going to get the area. So, in fact, it might be that, once you think about this enough, you're familiar with it, but at least the first time you encounter this derivation, you might say, how did we guess the right analytic continuation? And, the point is that we knew actually that we wanted, the Ryū-Takenagi formula was conjectured before, and this, the derivation came several years later. So we knew that we wanted to show that, there should be a minimal surface and we should get the area of the minimal surface. So because we knew we were going to get the area, that's a strong check on what is the analytic continuation that we need to do. If we had not known about the area formula before, it would have been very unlikely that we would have used this path integral and done this replica computation and derived the area formula. It's more the fact that, we knew the area formula, we already had hundreds of checks of the area formula. And then, one can use the path integral to say, look, here's the right, here is, you do this path integral, you set up this computation. Now you can, we know what the answer has to be. So, that gives you a strong justification for the analytic continuation that you're writing down. And then you can use it to get the area. But 0.5 is actually, is just, it's not a point about the derivation itself. The points 1 to 4 are actually how the derivation is carried out. I won't go through the details of the derivation because it will take us too far away from the main thread. But I just wanted you to keep this in mind. And for those of you who'd like more details, I'd refer you to the original literature of this. Okay, so that's what I wanted to say so far about the entanglement entropy in the CFT itself. I now want to move on and discuss the setup where I-lengths are relevant, which is when you have CFTs that are coupled to baths. Okay. So far, we've been talking about computing the entanglement entropy just for regions of the CFT. And of course, we could take a region of the CFT and, we could take some cylinder. And in the CFT, in the bulk, we could have some black hole also form. Maybe you have some black hole which forms. This is my drawing of a black hole. So we had some dust in the past. And then we formed a black hole. When you formed a black hole, some horizon developed. This is my horizon. Okay. So we have some cartoon of a black hole formation. And of course, in this setup where you have a black hole that forms in the bulk, you can still ask questions about the entanglement entropy. So, we could take some region, like maybe some region here. And, maybe we could call this region R, and we could compute the entanglement entropy of this region R. And we could even ask how this entanglement entropy varies with time, and such computations have been carried out. And of course, we could also ask what is the entanglement entropy of the entire boundary. Okay? So if you wanted to, in particular, check unitarity, then we could also ask what is the entanglement entropy of the entire boundary. And in fact, the Ryu-Takenagi formula correctly tells us that the entropy of the entire boundary remains 0 for all time. So even if you have a black hole formation and you try and ask, what is the entropy of the entire boundary, even if you have a black hole in the bulk, or you might have a small black hole that forms and evaporates, the entropy of the entire boundary remains 0. And so the entire boundary always has information about what is happening in the bulk. And this is, of course, consistent with what we were saying previously, what we spent some lectures discussing. So, of course, it's consistent with ADS-CFT because ADS-CFT tells us that, the CFT always has information about the bulk. And it's also consistent with what we were calling the principle of holography of information, because that also tells us that, if you compute a small time band on the boundary, that has information about the bulk. And so the fact that the entropy is 0 is consistent with all of this. Okay? But now you could ask a slightly different question. Okay? So this is a computation you can do, and as I said, it already tells you that the evolution in the bulk is unitary because it's telling you that a pure state is evolving to a pure state. If a pure state had evolved to a mixed state, then the entropy would not have remained 0. And so if you believe the Ryu-Takenagi formula, and then it's already telling you that a pure state evolves to a pure state, and therefore it tells you that pure states don't evolve to mixed states, even if you have black hole formation and evaporation in the bulk. And so that's a nice check of unitarity. But now you could ask a slightly different question, and the different question that is asked is as follows. In fact, we already discussed this a couple of weeks ago, but let me just recap before I write down the formula. The different question that we could ask is the following. You see, let's take in the bulk, not just a theory of gravity, but let's take a gravity, and let's take the matter sector also to be a conformal field theory. This is so now the bulk is d-dimensional in what I'm saying. You will see why in the next lecture we're using these conventions, which are slightly different from the conventions we've used previously, where we said the bulk is d+1 dimensional. In what we are saying today, the bulk ADS is d-dimensional. And of course, we know that this whole setup is dual to some CFT, but in d-1 dimensions. And remember, of course, time is running up on this graph. Okay. And now we could take this CFT d-1 that we have on the right side of this picture, and we could couple it to the same CFT d that lives in the bulk. Okay. So we have gravity plus a conformal field theory in ADS, which lives in the bulk. This whole thing is dual to a conformal field theory in one lower dimension that lives on the boundary of ADS. But now we are free to take this conformal field theory. This conformal field theory might just be some system that lives in the lab. So we could take the CFT d-1, and we could put some wire or put some coupling so that it gets coupled now to the same CFT d, but without gravity. The CFT d-1 might have very high central charge, because in general, holographic theories have to have large central charge. This CFT d in the bulk also will have large central charge, but maybe not as large as the CFT d-1. But the point is that when you couple the CFT d-1, which is living here, to the CFT d, in fact, the CFT d has more degrees of freedom because the CFT d just lives in one higher dimension. So just the volume effect means that the CFT d has more degrees of freedom. And therefore, if you have some energy that initially lives in the CFT d-1, that energy will tend to flow into the CFT d. And purely in this setup that we have on the lower part here, in this setup, notice that there's no gravity anywhere. We could take some imaginary interface, let's call this interface, and let's call this region R. So this region R is some region R in this CFTD without gravity. And we could ask, what is the entanglement entropy of the region R? Okay. So notice that the question we are asking now is slightly different from the question that we asked yesterday and in the first part of today's lecture. It's slightly different because the CFTD itself does not live on the boundary of ADS. The thing that is living on the boundary of ADS is the CFTD-1. But I just took the CFTD-1 and maybe the CFTD-1 was living in my lab, and I coupled it to a system in higher dimension. So now I have in the higher dimension a system, a CFTD that lives on a half plane, which is terminated by some defect on which you have a CFTD-1. And this whole system is a non-gravitational question, and it's a perfectly well-defined question to ask, what is the entropy of the region R? Okay. Okay, great. Now I can draw another picture for the same setup that we have here. So let me draw another picture. So, I could take this picture and I could replace the CFTD-1 that you have here with this part of the graph. So I could draw another picture for this. You could draw a picture for this, which said, where I basically take this part of this duality and I take this part that I've coupled things to, okay, great. So this is another picture for the same system, right? So it's the same system, but I've drawn another picture for the system, right? Now in this picture, I might have, maybe a black hole in the bulk. Right? I might have a black hole in the bulk, So like the black hole I drew previously, maybe there's a black hole. Oops. Here's my horizon. And maybe this black hole evaporates. And now if I turn on the coupling in the right way between the CFT d-1 and the CFT d, I can turn on a coupling that corresponds to what are sometimes called transparent boundary conditions. And what that means is that I can turn on a coupling between the CFT d-1 that lives on the boundary of the CFT, or of the space in the left half. I can turn on some coupling in such a way that if I think of a classical solution where you have some particle that comes to the boundary, this particle can kind of evolve on smoothly. So transparent is not something that's always made very precise, but roughly the idea is that you want a way so that, a classical wave which comes and hits the boundary of the first ADS can kind of smoothly continue on the other side. Of course, the action on the right side is different because the action on the right side does not have gravity. And so some degrees of freedom cease to exist at this interface. But nevertheless, if you turn on the right couplings, you can set up these boundary conditions which approximate transparent boundary conditions. And now it looks like we have a setup where this black hole on the left can evaporate and can send energy into the CFT on the right. Okay? So this is the setup that is relevant for all the proposals in which the island formula has been used. Okay. Now let me say a few things which I think are important in terms of interpretation before I say a little bit more about the formula itself. I think sometimes, so we will now compute how the entropy of this region R is. That's what the island formula does. The island formula is a generalization you can think of the Ryu-Takanagi formula to this setup, where the CFTD is not living on the boundary of ADS, but rather it lives in this way where it's coupled to the boundary of ADS. And yet we say that we can generalize the formula, and the derivation goes in the same way that I indicated previously. It's a generalization of the Maldacena-Liukovitz derivation. And the claim is that we will find a way to compute the entropy of the region R, and this is the entropy that will obey a page curve. But I should say a few things which I think are important in the question of interpretation. Sometimes, by looking at this picture, people say that we are computing how information emerges from the black hole. Okay, but I think that's a little sloppy. So I think this does not. I think it's a little sloppy to say that. So people say that information is emerging from the black hole. The reason that's a little sloppy or a little inaccurate is the following. The reason is that we already know that from all the discussions that we've been having that in a theory of gravity, remember here gravity is dynamical, information is not localized the way it is localized in ordinary quantum field theories. And therefore, we already know, and this is already clear also from the picture we had previously, that the information was already present on the boundary of the first region. Okay? So even before we turned on the coupling, the information was already present here. So really, if you wanted to ask a question about what the information transfer happening is, then you should think in terms of this picture. This is the picture below, which clearly tells you what information transfer is happening. And the information transfer that is being computed is an information transfer between the CFTD-1, which you can think of as living on the boundary of the original ADS, and the CFTD. There is no information transfer that's ever computed between how the information emerges from inside the black hole to outside the black hole. And these computations that are done are all perfectly consistent with the idea that the information is always outside. So let me just put this figure here, let me rescale it. Okay. So I think if you wanted to think of where information transfer is happening, it's useful to think in terms of the picture on the top right. There is never in the gravity setup a computation of information coming inside or outside a black hole. It's always how information is transferred from the boundary of ADS to the conformal field theory, which is also non-gravitational. So it's important, and as I emphasized also yesterday, questions of entanglement entropy are well defined in a non-gravitational setting, and the question we're asking is a well-defined mathematical question, and it's defined in a non-gravitational setting. But there are these are just words; they don't actually go into the computation in any way, and I just think that these words one should be a little cautious about. Okay. I think one should. There's another thing which I think one should be a little cautious about. And the second thing, these are again not relevant for the direct computation, but these are words that go along with it. And that is that these computations show that the evaporation of the black hole is unitary. But in fact, if you wanted to check the evaporation, the unitarity of the evaporation of the black hole, we already knew that from the fact that the entropy of the system without the coupling to the CFTD was always 0. So if we just wanted to check the fact that this gravitational setup that we had, or this place where gravity is dynamical, was obeying a unitary time evolution, then we already know that, because we know that if you didn't have this coupling, if you forgot about the CFTD, then I could compute at like T1 and T2 and T3. I could use the Ryu-Takanagi formula, in fact, to compute the entropy, and I would find that the entropy would always be 0. So S of T1 is S of T2 is S of T3 is 0. This is true without coupling. If I have the coupling, it would not be true. And this is already a check of unitarity. Okay, so this already shows us unitarity. So the fact that you will see a page curve and that we will see a page curve is not directly either a check of unitarity or a check of the fact that information is emerging from a black hole. But it is nevertheless a very interesting question. So the question is already interesting because it's a question of, how do you generalize the computation of holographic entanglement entropy to this different geometric setup where, the CFT or the region doesn't live on the boundary of ADS. And it's remarkable that one can find an answer. But I think that, it is neither a check of unitarity nor a check of how information emerges from a black hole. Okay? So I think that if you wanted to show unitarity using the RT formula using path integrals, you'd already have this check. Okay, so that being said, let me now try and explain what the formula is for the computation of the entropy of the region R. I'm actually going slower than I wanted, but I think we should be able to do this. So let me, okay. So let me try and
Suvrat,
the question.
That's asking that the entropy is always 0 for small black holes.
Yeah, and also for big black holes.
Okay.
Is that the question?
Yes, that was the question.
No, the entropy is actually also 0 for big black holes. You see, so so we have to be careful when you apply the Ryu-Takanagi formula. If you apply the Ryu-Takanagi formula for a black hole, for an eternal black hole, then the Ryu-Takanagi formula will give you the horizon area, which is the context in which it's often computed. But if you apply the Ryu-Takanagi formula to a black hole of the kind that I've drawn, my cartoon on the left-hand side, which is a black hole formed from collapse, then it will always give you 0. And the point is, if you take the entire boundary, there are always some choices of surface that you have. One is some surface which always stays very close to the boundary, which has like 0 area, and the other is the surface which is the horizon. So you have to choose which one is correct. And this homology constraint that I mentioned yesterday is important in choosing which one is correct. But indeed, for the case where you have a big black hole which is formed from collapse, the entropy always has to be 0. If it was not 0, that would be an inconsistency with the Ryu-Takanagi formula. So people, in a different context, the entropy is the horizon area, but that's for an eternal black hole. For a black hole formed from collapse, the entropy of the entire boundary is always 0. Does that answer the question?
Yeah, thanks.
Okay, great. Okay, great. So let me now explain the formula. My figure is becoming a mess, but okay. Let me see if I can rescue my figure. Okay, so how do we compute this? So we have this region R that we want to compute the entropy of, and the idea is as follows. Okay, So first, extend this to like a Cauchy slice over the entire geometry. So because we have this picture where we have an ADSD, and because we're going to use holographic techniques, you can extend this to some slice which runs over the entire geometry. Of course, here, remember, this is the part which has CFTD, no gravity. Here you do have gravity, but anyway, we can still think of this Cauchy slice. And then the formula is that if you want to compute S of R, then, what I drew right now is not a Cauchy slice because it's running through the singularity. So let me get rid of my singularity. Okay. Here's my Cauchy slice, and we don't know what's happening in the bulk. Okay, so if you want to compute S of R, then the formula is as follows, and this formula is derived by doing this replica trick that I explained previously. The formula is that it's the same min x that we discussed last time. But now the formula instructs us to consider all possible islands in the interior. Look at the area of the boundary of the island divided by 4G. And then take the semi-classical entropy of R union the island and minimum, and take the minimum and the extremum of this. Okay. So by island, it means that you take this Cauchy slice, and now you're allowed to consider any region in the Cauchy slice that could be disconnected from R. Remember, so this is the new aspect of this formula. Remember earlier we said that, you know, when you were taking these bulk regions, there was a homology constraint that said that the bulk region had to be anchored on R. Right? So here, the bulk region is not going to be anchored on R. The bulk region is just somewhere in the bulk. It's some island. Maybe it's this region. Okay, so say it could. This is a possible island. Okay. So you take you take the orange region, or you take some other region. For every such island, you compute these two terms. You compute the area of the boundary of the island. You divide that by 4G. But now you do a little bit more. Because you now need to take the semi-classical entropy, and notice this is the second difference with the original Ryutakinagi formula. The first difference is that this is not anchored to R. So that's difference one. The second difference is that we have this thing which we are calling the semi-classical entropy, but we are applying this notion of a semi-classical entropy not just to the bulk, but also to this region R, which lives in the non-gravitational region. Okay? So S semi-classical is also being applied to R. Okay? So notice that both of these are different features from the kind that appeared. Both point 1 and point 2, which I've written, are different from what appeared in the original Ryutakinagi formula. But the claim is that for this kind of a geometric setup, where this region R is not directly touching ADS, this is the correct procedure to compute the entropy of the region R. Okay. Okay. Is there? Let me also define what S semi-classical is. So I'll just write down what S semi-classical is. So this S semi-classical, one has to be a little bit careful about what this is, but this S semi-classical is the entropy as computed using the rules of QFT in curved spacetime. So not computed, using the full gravity theory in the bulk, but it's some approximation that is often defined. So this is using the rules of QFT in curved spacetime. Okay. In fact, this S semi-classical is a slightly tricky and subtle object, which we will explain when we come to specific examples. But I'll explain when we come to a specific example what are the properties that we want from this S semi-classical. But roughly, we want something that is not the full fine-grained entropy of the region R, because notice what we have here, we have the fine-grained entropy of R. On the right-hand side, we also have an entropy of R, but that entropy is a less fine-grained entropy. It's some coarse-grained version of this entropy, which includes R and also this island in the bulk. And the claim is you take these two combinations and then you extremize them and you take the minimum, and that gives you the correct answer for S of R. Okay? So I think I have, in 5 minutes, let me just try and explain the broad idea for how this gives the page curve, and then we'll do details next time. Okay. And I think that broad idea will also help to explain what this semi-classical means. So let me actually redraw my figure. So this is the gravity region. This is the non-gravity region. This is my interface. And this is my region R. Okay. So initially, let's say we had some black hole here. Okay. So we have some black hole which is forming, and we have like radiation coming from here. Okay. So since I have only 5 minutes, I'm just going to give a broad picture, and then we'll do details next time. So when you have radiation that is emerging, in this radiation, so this is also non-gravitational. This is the boundary of ADS. This radiation crosses the boundary of ADS with these transparent boundary conditions, and it enters into this region. Now, initially, if we had set up things so that this bath, this non-gravitational bath that we had was in the vacuum, then we expect that, you know, the entropy of R is just what you would compute for the semi-classical entropy of radiation. So let's say, you know, we weren't careful about the fact that gravity stores information differently, and we just took some 2-point functions and tried to compute an entropy with that. We would get that the entropy was thermal, and in fact, at early times, that entropy would be also correct. That would also be the correct entropy, because there wouldn't be enough time for, you know, all of these other subtle effects to become important. And so that the entropy, the initial thermal entropy that we would get from a semi-classical computation, would in fact be the correct entropy for the region R. And so in the initial stages, the island does not win at all. The island surface is not important at all. Okay. So at early times, we'd have S of R, and it would just grow at early times. Okay. So at early times, we see that we have S of R, and this S of R is just given from, you know, the naive expectation that Hawking had, which was that this entropy should just grow. It's a thermal entropy. It's an entropy of some thermal radiation, and as that radiation is entering this non-gravitational region, you know, it's adding energy where there was no energy before, and so it's also carrying with it entropy. And so the entropy just grows. Now, what do we expect from this S semi-classical? Okay. In general, we expect from this S semi-classical, which is coinciding at early times with S of R. So we expect from S semi-classical that it increases monotonically until the black hole totally evaporates. But the second thing we want from this S semi-classical is that the S semi-classical for the entire Cauchy slice is 0. Okay. So this is how we would have thought about, you know, this is how in some sense Hawking was thinking about entropy. And that Hawking was saying that, you know, if I took some Cauchy slice of this kind, then, you know, S of R is something that would keep growing because there's some information on the Cauchy slice that would get lost in the black hole. But if I took an entire Cauchy slice at some point, and, you know, I didn't trace over the region inside, then the entropy of that entire Cauchy slice would remain 0 at all times. And so that's why what we expect is that we expect these two properties from S semi-classical. First, that it increases monotonically, and second, that for the entire Cauchy slice, S semi-classical is 0. Okay. Okay. Now, it's not entirely clear how we should define, or, you know, S semi-classical instructs us to do something which is slightly coarse-grained. I think this S semi-classical has not been defined entirely precisely. But we will see that as long as we define a quantity, which in some cases we can define more precisely in some examples, as we'll discuss next time, which obeys these two properties, we see that the general picture of the page curve will emerge rather broadly. And let's say we assume that these properties are true, then let's see what happens at late times. You see, at late times, we still have this region which has gravity. But now and this is our Cauchy slice. But now notice what is happening. At some point, S of R, which was growing, becomes extremely large. And it might happen that, maybe we have a horizon here. It might happen that an island develops in the interior. And the moment you write down an island of this kind, you have to pay a cost in terms of area. Let me remind you what the formula was. This was the formula. And if you write down this pink island and you try and ask whether this island can contribute at late times, you see that you have to pay a cost because there's an area over 4G term, which is a large term. So in general, introducing an island is expensive, and it could lead you to believe that maybe, it's hard to imagine how the island could win this min. But in fact, at late enough times, it might happen that the radiation in this island purifies the radiation here. If it purifies the radiation in R, then you see the island might have a large cost in terms of area, which we see here. But on the other hand, it might also reduce S semi-classical by a significant amount. Remember, and the reason that works is because we said that the entropy of the entire Cauchy slice is 0. And so we do expect that, one part of the Cauchy slice will purify another part of the Cauchy slice. And so it could be that even if the island is expensive in terms of area, it, compensates that expense by reducing sufficiently the S semi-classical of R. Okay. And indeed, we expect that this happens once S semi-classical of R starts growing large enough. And that turnaround, in fact, is precisely at the page time. Okay. So after the page time, the island wins because the reduction in S semi-classical compensates for its area. So therefore, we expect to see for S of R, first a curve that grows according to S semi-classical, and then after the page time, a curve that comes down. Notice it's very important that this had to happen if the entropy formula was correct, because we were asking a question which is precisely the question that Page asked, which is, you have a system which lives in the lab, you divide it into two parts, you have energy transfer from one part to the other part. It better be the case that the entanglement entropy of one part of the system or of both parts of the system obeys the Page curve. And indeed, that happens because on this part of the curve, the island wins. Okay. So we see that we have some way where, we asked a non-gravitational question, but we have some way to holographically compute the entropy that we are getting. And this entropy is clever enough to ensure that what had to happen does happen. And the way it happens is that initially, the island saddle point or the island does not contribute because S semi-classical just wins. But at late enough times, the area expense of the island can be compensated by the fact that it purifies the radiation. And that's what gives you the lowering part of the Page curve. Okay. So this is, and of course, as time goes on, the island shrinks because the horizon itself shrinks, and there's less and less stuff that's left behind in the original black hole. And so eventually the entropy of the island goes down to 0. And that is the broad picture of how we expect the page curve to emerge. Okay. So I haven't in this last part given you precise details. We will next time discuss a more precise setup. In fact, for these setups where you see a page curve that rises and falls, we always need to wave our hands a little bit, although this is the broad picture, what I just outlined. So we will next time, in fact, consider the eternal black hole, where we'll outline a specific puzzle and also explain how the island proposal resolves that. So I went a little bit over time. I'm sorry for that, but I just wanted to complete this part. So we can stop here actually, and I can take questions if there are some questions.
Yeah, I got a question, maybe relating back all the way to the gravitational path integral.
Okay.
Because it wasn't maybe entirely clear for me how I should. Yeah, I mean, for the we discussed how in a gravitational Hilbert space the Hilbert space doesn't factorize.
Yes.
But how are the boundary conditions defined in this gravitational path integral there? Is it just for a region, or is it for the whole space-time?
So these boundary conditions, yeah, so maybe here. Yeah, so this is the entire boundary. Of course, this boundary is replicated, but in most parts, the fact, the complicated part of the boundary is near this region R, right? Because you cut the boundary on this region R, and then you glue it together. But now you have some entire boundary, which is like some in-sheeted cover of the original boundary, and that's the whole boundary. And now you need to find some bulk solution that matches with this boundary. So it's the entire boundary that's replicated, but of course, in some parts it just looks like it did earlier, but it just looks like there are n copies. But in some parts, these n copies are glued together, and that's on these regions R.
Okay. Yeah, that's clear. And maybe another question, which was about the last part about the entanglement wedge reconstruction.
Yes.
Because if the area term appears, I think this is also related to the subregion duality.
Uh-huh.
But I'm a bit confused how we should see the principle of holography and the factorization of the gravitational Hilbert space there with the area term appears. I mean, it's not entirely clear for me.
Okay, so I'm not sure I understood the question. So are we still talking about the first? So we're not talking about islands right now. We're not talking about islands. We're just talking about the original entanglement wedge reconstruction. Or are we talking about islands or?
Yeah, but well, also about the. I think for first maybe the entanglement wedge reconstruction.
Okay, so now yeah, good. So you see, in this situation, actually, the fact that the Hilbert space doesn't factorize is not so relevant because we are never taking a geometry where we are taking the inside and the outside. You see, it was very important that when we argued this thing about factorization, we said, look, the Hilbert space never factorizes into the inside of a ball and the outside of a ball. So if I had drawn this kind of a circle and I had said, look, let me talk about the outside and the inside and compute the entanglement entropy of the outside, that would always be a bad thing to do because we said the Hilbert space doesn't factorize, and we spent a lot of time on that. But if I want just to draw if I want to define some Hilbert space for this region, what the thing I have shaded, then there is, in fact, this has not been made precise. It's one of the things that should be made precise in entanglement wedge reconstruction. But you see, there is plausibly a way to define a Hilbert space which does factorize in terms of the entanglement wedge and its complement. And the way that happens is if you want to write down a local operator at this point P, you just dress it to the region R. So, there is a place for Wilson lines to end. And that is because this region, this entanglement wedge always also includes a part of asymptotic infinity. If you just take a purely bulk region, then it's clear the Hilbert space doesn't factorize. So if you take a region in the bulk, which is surrounded by another region, then there's no factorization. But in this situation, in the entanglement wedge, we never have a geometry of that kind. We always have a geometry that includes part of asymptotic infinity. And that means that I have a hope of defining an operator phi of P by taking its Wilson line and by dressing it to this part of the boundary. And so there's a sense in which I can define another operator here, phi of P prime, And I can expect that phi of p and phi of p prime will just commute exactly because this operator I addressed to this part of the boundary and phi of p I addressed to the region R. And so in entanglement wedges, the geometry is never of the kind that we discussed previously, where you had one region being surrounded by other. And that's important for the prescription to be consistent. Otherwise, it would not be consistent. And you can check that you can never find an entanglement wedge where the wedge is a complete, there's a ball and the wedge is the outside of a ball. So the wedges always have this kind of a geometry of the kind I've drawn. And that's why there's a sense in which you would expect that you can write down operators phi of p, which commute with operators phi of p prime, which are outside the wedge, by addressing them to different parts of the boundary. So does that answer the question?
Yeah, but then directly for the island setup, I feel like we have this kind of.
Good. Good. So for the island setup, you're right, and that is indeed something that should be. It's a valid observation, and it's something that you're right should be clarified more. We'll say a few more things when we discuss the island setup. One thing is that you can think of this island setup, this is a preview of what we'll say next time, in one higher dimension, in which case it really becomes just a normal entanglement wedge. You can think of the setup where the islands are not just holographic, where the CFTD is also holographic, and then the whole thing goes into one higher dimension, and then there's a sense in which this contradiction does not appear. It's also true, by the way, that these theories which have islands are slightly different. I mean, there's a subtlety which I didn't mention, which is that you can check that in setups of this kind, the bulk graviton always picks up a mass. So, the theories of gravity that we have here don't actually remain ordinary theories of gravity. They're unusual theories of gravity in that the bulk graviton all picks up a mass. And maybe that is important in localizing this information. But you're right. This is something that I'm also uncomfortable with, and I don't actually have a good answer. That the island proposal appears to give you the right entropy, but if you take the island proposal more seriously and you say there's an entanglement wedge reconstruction, then you do have, for the first time, which you'd never have had previously in ADS-CFT, a situation in which you have a wedge which is the inside of some region. And you could have well asked, why doesn't this region have information about the inside of the island? It may be that the answer lies in the fact that you always need to embed this in one higher dimension. It may be that the answer lies in the fact that the graviton has to be massive. But I actually don't know what the answer to this is. And I think it's something that people haven't thought about very carefully. And it is an unusual aspect of island entanglement wedges, which doesn't happen otherwise. So
just out of interest, is your intuition then related to the fact that your principle of holography in flat space was only for massless mode? So when we have a massive graviton that we
I'm saying something pretty vague actually right now. So this is I don't know how to make it. It's certainly true that when you have massive gravity, that gravity could be different. It could behave differently. Because so just to say, the reason gravity becomes massive is because the stress tensor on the boundary is not conserved. So if you think of the stress tensor that is dual to the graviton, the stress tensor is not conserved, and therefore the graviton picks up a mass. So maybe massive gravity behaves differently, but actually I'm just guessing. I don't have something precise. I'm just pointing out some ways in which things are different. It could be that maybe you always need a holographic CFT, or it could be that you need a massive gravity. In some sense, you're right that there is a. I mean, the question is pretty sharp. The question is, if you want to write down a local operator on the island, how do you write down an operator here without addressing it to some region asymptotic infinity, where the island doesn't include a part of asymptotic infinity? So the Wilson line has to somehow jump, and it has to reach here. So how does it do that? If there was an extra dimension, it could do that, as we will see. This is I don't have a good answer to that question. And I don't think actually anyone has a good answer to that question.
Okay, cool.
I mean, it's an absolutely correct and important observation that there's something unusual. So I didn't mention it because I didn't want to go into that subtly. I think it would be very interesting to be able to understand how the Wilson line in the island gets dressed. I mean, how does it reach this non-gravitational region? Because it's surrounded by its complement.
Hi, Suvrat.
Hi.
So this graviton becomes massive only after you remove the extra dimension. Is that
The graviton becomes massive in what?
only if you get rid of this extra dimension where the entanglement wedge is really connected?
So the graviton that lives on this 4 dimension is always if you just think, so right now we don't have an extra dimension, right? We just have some CFTD minus 1. But now the point is that in this ADS setup, the graviton is dual to a stress tensor which lives on this boundary. Okay, this is the stress tensor of the CFTD minus 1. This stress tensor, you see, you could have asked, what is the analog of the fact that the graviton is not massive? It's the fact that the stress tensor is conserved. The stress tensor has a certain conformal dimension. Why does it have that conformal dimension even after you turn on interactions? Because it's conserved. So there's, it's in a short representation of the conformal algebra, and that's why, it doesn't pick up an anomalous dimension. But if you couple it, then, it stops being conserved, because now this stress tensor is not preserving energy. It's losing energy. And therefore, it can pick up an anomalous dimension. There's nothing that could prevent it from picking up an anomalous dimension. And when these models were analyzed, in fact, many years ago, it was found that, in the bulk, some one loop term will give the graviton a mass. In the setup that we have here, the theory of bulk gravity is massive. It's not a massless theory. So it's not ordinary gravity. It's a slightly unusual version of gravity.
But once you embed this into the higher dimension, the gravitons there are not massive.
So there will be a higher dimensional graviton that will not be massive, but the graviton mode, which is localized, the way this is embedded is, which we'll discuss next time, is that there's a brain world. This dynamical gravity theory will live in some brain, and then there'll be a non-gravitational boundary, and there'll be a higher ADS-D plus 1. So of course, in the higher ADS-D plus 1, there is some higher dimensional graviton, but the mode that is localized in the brain will be massive.
Okay.
So there'll be some mode which will be localized in the brain that will be massive.
So I want to ask something naive, so if I was just thinking about some flat space observer, like the Rindler observer in flat space, and I wanted to calculate the entropy of the whatever the detector detects or something, should I be able to give an island-like formula? Should you be able to give it
island-like formula? I don't think so. What we have here is a setup where gravity has really been switched off. So, there are, of course, papers in the literature where people just use an island-like formula, but there's no real justification for that. Here we have ADS, it goes to asymptotic infinity. You couple it to a region without gravity. If you're just in flat space, in fact, we can say more than that, right? In flat space, we have an argument saying that the region outside really does know about the region inside, if you have massless gravity at least. And so, you don't expect to see the page curve in flat space. We'll discuss a little bit whether, there might be an approximate sense in which you might see the page curve, but really, if you look at the fine-grained entropy of R, you really should not see a page curve. And there is actually no justification
I didn't
for such
a
situation.
I meant something similar, like a real flat space QFT, no gravity at all.
Oh, flat space QFT, no gravity.
A Rindler observer who collects radiation from the Rindler horizon.
Oh, you mean no gravity at all? Then, of course, the island formula can't work either, because, the island formula, the fact that something funny is happening if you just had no gravity, then this would not make any sense, because, where did this area over 4G come from? There's no,
Yeah, I know there's no G Newton to start with, but I'm guessing even here, the G Newton you could replace with maybe the mass of the graviton or whatever, right?
No, I don't think so. Because there's this also, the fact that this region R somehow knows about the island is some very non-local effect, right? It's the fact that the region R knows about something that's happening very far away. And that would never happen if you did not have gravity. So if you just had no gravity throughout, then this would not work. So to expect that the island formula will work, you have to have some setup where there's at least gravity in some region and no gravity elsewhere.
No,
But just the
Rindler observer collecting radiation, and he would at some point reach his entropy would rise, and I should expect a page curve for that even.
So here you have to, so we'll discuss that a little bit next time. You have to first have a setup which has a finite number of degrees of freedom. The thing that will happen in the puzzle that we'll reach next time is that the CFTD minus 1 in the end has some finite central charge and has some finite number of degrees of freedom. And yet it looks like there is some quantum field theory in the bulk. So somehow there has to be a way in which all those, infinitely local degrees of freedom get cut off. With the Rindler observer, there is first of all no radiation to collect, right? There's no radiation that is emerging. But of course, you could take some accelerated observer, and maybe the accelerated observer collects radiation. I'm not sure exactly what you're referring to, but
yeah, I meant an accelerator observer who has a Wendler horizon, and then he will detect radiation right from the horizon.
Yeah, but there's no island formula. I mean, there's not even a contradiction that, if you just take, so maybe one way to say it is, let's say you just take like flat space and you start taking like funny Cauchy slices, which you could take, right? You could take Cauchy slices that bend up in some more and more steeply. Then you would find at some point some entropy which grows in some unbounded way, and it would not be in contradiction with anything, because it's not like the region in the middle is described by something which has a finite number of degrees of freedom. So you could take regions and boost them in some funny ways, or do some funny things to the Cauchy slices in a way to get an ever increasing entropy. But you would not get a puzzle. So if you just had QFT and no gravity, there would be no puzzle to start with. I mean, yeah, it's clear, right? Because you can't have a resolution of this kind. There's no.
Okay.
You could ask a different question. You could ask a question: if you had a lump of coal which was evaporating, then you do expect to see a page curve. And how does that page curve come about, right? And there, of course, that page curve is just a page curve. People say page curve S semi-classical. So it comes about without islands entirely. It's just that S semi-classical itself obeys a page curve. I don't know if that answers the question, but.
Yeah, I was wondering whether if I just say that since the dictator has some finite Hilbert space and like, okay, something like that, if I would run into a page.
I mean, we can set it up more. You can set up the puzzle more precisely, but whatever the resolution is, it can't involve islands.
I know. I was just asking would this page need for page curve run me into a similar argument, whether I need a purification which is inside the Wendler horizon or something.
Yeah, I think it might be, if you were to set up the argument more precisely, it would help. We could then discuss. I'm sure. I mean, you're right that one could probably set up puzzles which would have a resolution, but yeah. So I think right now I'm not understanding entirely what the puzzle you have in mind is.
Okay, so okay, I'll maybe ask you later.
Yeah, sure, great. Yeah.
I had a follow-up question on this around the lump of coal example, because I'm a bit confused though, because we keep switching between two perspectives. But from the perspective where you have a CFT D minus 1 coupled to a flat space CFD,
right? Then
the fine-grained entropy should always be the semi-classical entropy, right? Because in that system there's no gravity. So how come that the region R at some point gets a gravitational interpretation, whereas we are just looking at the CFT?
So this entropy is always. So this is not semi-classical. This is just the entropy R. So you could take the system, put it in the computer, and just compute the entropy R, and you would get what you expect. This is some wrong answer for the entropy of R. Like, this is some answer when you say semi-classical. This is the answer where you take this region R, you think of it as being part of this ADS. So you think of R union ADS, and you do some wrong computation inside ADS in a way to get some entropy for the region R, which is not the correct answer for R. If you really thought of R in the original setup and you just did some CFT computation of R coupled to a CFT D minus 1, you would get the left-hand side. That's the left-hand side. The right-hand side is something else, where you say that you take some metric, you write down this metric on this thick Cauchy slice, which is some metric which has ADS in one part and maybe some R in some other part. This metric that I have here, and then on this metric, maybe you do some one-loop computation or you do something, and then even if so there's some computation where you don't do an entirely fine-grained computation. But that being said, I have to say this is another aspect which I think it would be nice to spell out a little bit more clearly what S semi-classical is. Let me give you an example where this can be made more precise. You see, one place where this can be made more precise is the 1 + 1 dimensional example. In the 1 + 1 dimensional example, we have some formula for the entropy of regions, and then you can just write down some geometry which is ADS here coupled to some flat space here. And then you could write down some formula in this more complicated geometry of the region R, which would be different from the formula you'd write down if you just had the CFT living on a half plane ending on a defect. Okay. So if you wrote down some formula for the CFT on a half plane ending on the defect, that would be the correct formula. But instead, you can think of this picture where you take it very seriously. You think of a CFT living on ADS and living here, and then you write down some formula which is not actually the correct formula, and that's the formula that's appearing on this side. Okay. So what appears on the right hand side is not the correct entropy of R. It's some coarse grain version of it, which is not the right entropy of R. Did that answer the question?
Yeah. Yeah, partly because from the perspective where we take an ADS space coupled to a flat space, I can understand the island formula.
Right.
But if we take the perspective from a CFTD -1 living on a flat space with a CFTD, then it seems to me you're only shuffling around CFT degrees of freedom.
Yeah.
So since you're only shuffling around CFT degrees of freedom in a non-gravitational region, how come gravity enters the picture
in the picture where you just had a CFTD, I got all my pictures mixed up, but if you just had a CFTD, then this is the entropy. So this is the correct answer. The point is, you see, you could have asked this question even for Ryu Takenagi. You have a CFT, you divide into 2 regions. How come you got, even we wrote down a similar formula also for Ryu Takenagi, where we said, where we had area of, I don't know if maybe it's the first formula I wrote down. Let's see. Maybe even before this. Yeah, here. You see, even here on the left-hand side, we have just a CFT entropy. This is a completely non-gravitational question. On the right-hand side, we again have something which we say is S bulk. We have once again something which is entirely non-gravitational, and then you say, well, but in some special cases, I can actually compute this answer by doing some computation in a totally different setup. And that's actually what we're doing here as well. We're asking a question which is defined in the CFT, and then we're saying, well, by the way, we can use gravity to compute what this answer is, which we can often do, right, in holography. We can often ask a question which is well defined on the boundary and use gravity to compute it. And this S bulk is actually very similar in spirit to what appears in the island formula, except for this difference, which is that this X doesn't have anything to do with this R. This X is some region in the bulk. Whereas in the island formula, the region that appears also involves this region R. So we have S of R appearing both in the left and the right in the island formula, which doesn't happen in the usual Ryu Takenagi formula.
Okay, can I then interpret this moment where the island starts to play a role as the moment where all these CFT degrees of freedom in R, first they don't have an holographic interpretation, but then as soon as you have islands appearing, this region R becomes holographic, and you can also view it as from a holographic perspective, and therefore you can include gravity.
Yeah, I mean, that's what the entanglement wedge proposal would say, that at the point when the island starts winning, this island, the degrees of freedom in the island are now described by the degrees of freedom in R. But it's really, they're just CFT degrees of freedom, but it so happens that now the entanglement structure of the boundary has changed so that some degrees of freedom in the bulk, which were earlier described by degrees of freedom somewhere else, are now described by degrees of freedom in R.
Yeah, okay, yeah, thank you.
Okay.
So there was one question in the chat. She's
Yeah.
asking, I mean, the island is not anchored to the region R, but is it not homologous to R either?
If you think in higher dimensions, there's the standard homology constraint that we will be able to impose, where the island will be homologous to R. Maybe I guess, since I've said it so many times, if you think in higher dimensions, which I think is actually is a very clean way to think about islands. Sorry. Yeah. Then the way it works is that you embed the whole setup in one higher, and this is R, and then this is the RT surface, and this is the island. And then this region is, of course, homologous to R, because so that's how you impose the homology constraint. So this is ADSD plus 1. This is the ADSD that we were talking about, and this is the CFTD that we were talking about. Okay. So now, yeah, go on.
So there is no way to see this homology constraint in the original setup, right? We have to use this double holography.
Yeah, I don't know of any good way to see the homology constraint in the original setup.
Mhm.
I don't know of any good way. Yeah.
Okay, I see. Thanks.
Are there any other questions?
Yeah, I had, one last question about this this perspective of the boundary CFT coupled to the flat space.
Yeah.
How do you sort of sensually take out the radiation degrees of freedom from the CFTD -1? Because the information of the bulk is always stored very non-locally on the boundary, right? So
Yeah.
how do you pick out particular CFT degrees of freedom that should correspond to the radiation?
You don't, right? You just turn on a coupling and whatever flows from the CFT flows from the CFT. So, the page curve is a very generic thing which will happen whenever there's exchange of information. So you don't turn on when we say transparent boundary conditions, that's some classical notion where the statement is you're trying to write down some coupling so that if you think of a wave which goes and hits the boundary, that wave induces a wave on the other side. But we're not trying to ask a more fine-grained question about how, for instance, you take the information in the radiation and you drop the information that lives in the gravitational degrees of freedom or anything like that. So we don't even try to make some distinction of this kind. We just turn on some coupling and then you see the page curve emerging. So you don't try and say, well, we're picking the information, the radiation, we're not picking the information that lives in the gravitational constraints. And that's why I think it's important that, it's a little misleading to say that we are computing the entropy of the radiation that's coming out of the black hole. We just are computing, we just have two systems which we couple together and energy flows, and we just compute the entropy of some region R. It's not like we compute the entropy of some specific part of the gravitational system, and there's no clear, there's no clear way in which we try and pick out the information that lives only in the radiation as opposed to information that lives in other degrees of freedom in the bulk. I don't know if that's what you're asking, but
yeah, no, exactly. That is I think exactly my point. But then it feels that still everybody talks about it this way, right? That this region R really is the radiation that comes from the black hole.
Okay, but these are words. I mean, they don't go into any computation. So as I said in the beginning, I think that the words that are used with this are sometimes a little. I think I agree that the words that are used with this are not entirely accurate. The computation is a precise computation which one can do, and then there are some words which one adds on to this, which I agree one should be more careful about, which I agree are not entirely accurate. So these words that the radiation, we are collecting the radiation from the black hole in this non-gravitational bath, which are the words which are commonly used, I agree are not accurate. That's not, I completely agree with that. It doesn't have any bearing on the computation we are doing, but it would be good to phrase things more accurately as well.
Okay, thank you very much for that. That clarifies a lot for me.